In this video, we are going to be covering the concepts from chapter 2 that we haven't covered to date and the beginning of chapter 3, specifically sections 3.1 through section 3.3. Let's now review the last topic that we talked about in lecture, which was based on the information that is given in each one of the boxes of the periodic table, how do we derive the information for the number of protons, the number of neutrons, and the number of electrons for a particular element? So when we look at the box for each of the elements in the periodic table, we see that there is a digit on top of the element symbol. That is what we know as the atomic number. And the atomic number, when we relate it to the subatomic particles, it equals the number of protons. But because we're talking about ground state elements, things that haven't lost electrons, this is also the number of electrons. This specific box, it gives you the symbol of the element. Below it, we have the full name of the element. And below that, we have a new set of digits. Now, this new set of digits is what we know as atomic mass. And the atomic mass, when we round it to a whole number, is one of the ways in which we can obtain the mass number for an element. In class, we actually did at least the first 2 rows for the in-class worksheet. So let's just review quickly the first row to see how it relates to the information that we have for the element beryllium. You see highlighted in yellow the information that was already in the table, okay? And then the other information that is there, we wrote it in. So in the first row, we were given the atomic number and the number of neutrons. Since we had the atomic number, then we can derive that, as you can see, the atomic number tells me the elements. That's how we know that we were dealing with beryllium. Having an atomic number, because it equals the number of protons and the number of electrons, that's where we get the value of 4 for the protons and the electrons. Because the number of neutrons were given to us, another way that you can obtain the mass number by adding the number of protons plus the number of neutrons. And as you can see, when we add 4 plus 5, that's where we got the 9. In parentheses below, I actually put the atomic mass that shows up in the periodic table. Okay? So we did a similar problem in the second row with chlorine. You can follow the same rules in order to understand how those numbers were obtained. The next section that we need to go over is the idea of isotopes and atomic mass. So let's first define what is an isotope. Isotopes are atoms of the same element, but they have different atomic mass slash atomic number. So when we utilize an analogy to understand isotopes, I like to use the analogy of if you go to the grocery store to buy vanilla ice cream and you go to the refrigerated section of your preferred grocery store, you may find that there's going to be different vanilla ice creams. You may have vanilla bean vanilla ice cream. You may have French vanilla ice cream. You may have home style vanilla ice cream. All of them are vanilla ice creams. It's just that they're different flavors. So think of isotopes as different flavors of the same element. In table 4.7, which is a table from a different textbook that I like to also utilize as a reference in this course, understand that it is illustrated different isotopes for the element magnesium. When it comes to the name of the isotopes, understand that it's going to be the element name followed by the mass number. And we can see here, because each of these are magnesiums, the number of protons is going to be 12 because that's the atomic number for magnesium. Now, since the number of protons and we're talking about ground state magnesium, that's why the number of electrons is also the same. Now, let's notice that when it comes to the number of neutrons, they're going to be different for each of the isotopes. So if you affect the number of neutrons for a particular atom, and since we learned previously that mass number slash atomic mass in general is going to be protons plus neutrons, then it makes sense that if the number of neutrons is different between the different atoms, then they're going to have not only different mass numbers, but also mass for the isotopes, just because of that difference in the number of neutrons. There's one more piece of information that is illustrated here, and that is percent abundance. Percent abundance tells us if we are actually looking for a sample of magnesium, what is the most common magnesium that exists out there? And as you can see, because magnesium 24 has the highest percent abundance, that's how we know that it is the most common. Another way that we can tell if we are just given the isotopes, which one is going to be the one that is the most common or in general have a higher percent abundance, then we can look specifically at the atomic mass for that particular isotope and compare it to the atomic mass that shows up in the periodic table. So for example, the atomic mass, let me specify, from the periodic table is 24.3050 AMU. So when we compare magnesium 24, 25, 26, you can see that magnesium 24 will be closer to the actual mass that we have for magnesium in the periodic table. Understand that even though in this course we're not going to learn how the mass that shows up in the periodic table comes about, understand that in general this mass that is in the periodic table is going to be taking into account the percent abundances of each of the isotopes, and there's an actual calculation that you can do to understand how, based on percent abundance in the mass of the isotope, you can calculate that value that shows up in the periodic table, but we're not going to do it in this course. Secondly, since isotopes exist, there is a notation that can be utilized in order to write them, and that is isotopic notation. And you can see on the right side of the slide how isotopic notation is illustrated. There are three components for isotopic notation. First, you write the element symbol. Then you're going to put digits on the top left corner and on the bottom left corner. The digits that are on the top left corner are going to be the mass number. And that mass number, again, it depends on the number of protons and neutrons that you have for that particular element. Then you have in the bottom left corner the atomic number for that element. So now, in order for us to practice, you can see that we have problem 2.16. This is on page 53 of your textbook. I have given you different isotopic notations for isotopes of different elements, and let's learn how to derive number of protons, neutrons, and electrons for the isotopes that are here. So let's do the first and second row in this video. First, we have an isotope of hydrogen. Remember, when it comes to isotopic notation, this is the atomic number. This value is going to be the mass number. So taking that into consideration, remember, atomic number gives you protons and neutrons. So this isotope of hydrogen is going to have 1 proton and 1 electron. Then mass number is going to be protons plus neutrons. So to find the neutrons, I'm going to do mass number minus atomic number. So that means that there is 1 neutron in this isotope. Let's also do the second one, the isotope for aluminum. Number of protons, 13 because of the atomic number. Number of electrons, also 13 because of the atomic number. Number of neutrons is going to be 27 minus 13. That means that this isotope is going to have 14 neutrons. So isotopes are actually very interesting, atomic species. And elements can have 1 or more isotopes. Now, when it comes to these isotopes, there's going to be some of them that have unstable nucleus. And when an atom has an unstable nucleus, one of the things that can happen is that it can emit small particles of energy, and we call that radiation. So you may be wondering, why would an atom do that? Well, when that unstable nucleus releases these small particles, it creates a more stable and lower energy nucleus. If there is a particular isotope of an element that emits a radiation in general, understand that this is known as a radioisotope. Here in the slide, we have different isotopes for carbon. We have carbon 12 first. In the middle, we have carbon 13. In the last box, we have carbon 14. You can see that carbon 14 out of the 3 isotopes that exist for carbon is the one that is radioactive. And this is by experimentation that is known that carbon 14 is radioactive. So out of all these isotopes, because carbon 14 is radioactive, that is going to be a radioisotope for carbon. Now that we know that elements that have unstable nucleus release particles, then let's learn the different forms of radiation that exist, starting with an alpha particle. So what is an alpha particle? Well, as you can see, an alpha particle is going to be a particle that is generated by what we call decay. So an unstable nucleus in an atom is going to decay and then release these particles. So in the case of an alpha particle, what is released is a particle that has 2 protons and 2 neutrons. And you can see this illustrated on this arrow in our figure. Now, having a particle that has 2 protons and 2 neutrons, it is identical to the nucleus of helium. That's why you see that specifically one of the illustrations that is utilized for an alpha particle is the isotopic notation for helium with a 2 plus charge, just indicating that the particle itself has a charge of 2 plus. But if you rationalize it, remember that it's formed by neutrons and protons are the only things that have charge. And since there's 2 of them, that's where the 2 plus comes from. So here we have an example of overall a particular atom that is undergoing decay and forming an alpha particle. So here we have the nucleus of uranium 238. That's going to be our element that is it's in a radioisotope, is what I'm trying to say. So uranium 238, as you can see, is going to release an alpha particle, and then understand that the nucleus that is generated once that occurs is going to be now a new element. This is thorium. And you may be wondering, wait, how is it that is forming a new element? Remember that the transition from uranium releasing that alpha particle, there were 2 fewer protons in the system. So if we track what is happening overall, we can see that we went from 92 to 90. Additionally, the mass went down, because remember that the mass of an alpha particle, because it's 4, then we went from 238 to 234. So now that there was a change in the number of protons, remember that having fewer protons changes not only the number of protons, but in turn, it changes the atomic number. And that change in atomic number, as you can see, created a brand new element that is going to have a more stable nucleus. There are other illustrations other than the isotopic notation to illustrate that alpha particle, and you can see them here. This symbol that looks like an A, it's actually drawn by hand like a little fish. That is just the Greek letter for alpha. Let's just go along and look at the other forms of nuclear radiation. The second type of nuclear radiation that you guys need to know is a beta particle. A beta particle is a high energy electron formed when a neutron in an unstable nucleus turns into a proton. Understand that overall, this beta particle that is released has a number of 0 in its mass because the mass is less than the one of a proton. And overall, it has a charge of -1. So here we have an example of a radioisotope that releases a beta particle. As you can see, here we start with that radioisotope for carbon 14. And this is its nucleus. One of its neutrons is turned into a proton. So in the isotopic notation, we can see how it went from a 6 to a 7. Remember, if you change the number of protons in here, because we turn into a proton, we are increasing the number of protons by 1. So if you increasing by 1, then you can see here how now we have that change in atomic number, which means that now we are dealing with something that is nitrogen, and there was a release of that beta particle that we see on the top of the figure. There are 2 more types of nuclear radiation that you guys need to be familiar with. The next one is a positron. A positron is similar to a beta particle, but it is produced by an unstable nucleus when a proton is transformed into a neutron. So, as you can see here, overall, the particle itself has a mass number of 0 and it has a charge of +1. So here we have an example of the formation of a positron. So our radioisotope is a radioisotope of oxygen, as you can see, oxygen 15. That's going to be the nucleus. So what we're talking about, remember always that all of this nuclear radiation is the nucleus of the atom. So in isotopic notation, we're talking about the radioisotope of oxygen. And a proton turned into a neutron. So overall, makes sense that since there was from proton to neutron, then we have one less in terms of the number of the atomic number because of the proton to neutron transition. Then remember that in this process, that's where the positron is emitted. So when we look at the daughter nucleus from the nucleus that releases that positron, we see that now that daughter nucleus created a nucleus that it is nitrogen. Just because, again, a proton turned into a neutron, so the number of protons went down. That means that the atomic number from where we started to what we form is different. The last type of nuclear radiation that you guys need to be familiar with is gamma rays. And gamma rays are a high energy radiation rays that are released when unstable nucleus undergoes a rearrangement. And this rearrangement is going to generate a more stable nucleus. Understand that the rays themselves are not particles, but the gamma rays are actually emitted with other types of radiation. Understand that when gamma rays are released, these gamma rays have no mass or charge. So the symbol that we use for them is here. I forgot to mention, this is the symbol for a positron. These are the symbols for the beta particle. In a few moments, I mentioned this, but just to make sure that you guys know, this is the notation for the alpha particles. Going back to the gamma rays. So when it comes to the gamma rays, again, they are emitted with other types of radiation. And I wanted to give you guys an example of how that occurs. So in the example that we have here, this is a radioisotope of cobalt. And when it undergoes the decay to form that gamma ray, we can see that along with the gamma ray, it also forms a beta particle. The reason why I know that it is a beta particle is because the designation in how the sentence was written for the generation of these particles, when I look at E0 on top, but then -1 is there. If I go back to my notes, oh, that is a beta particle. And overall, understand that in this process, we can observe specifically that since a beta particle was the one that was created, notice what happened in the atomic number. We went from 27 to 28. So you may be wondering, why is there an increase in the atomic number? Well, remember, beta particles are the transitions from a neutron to a proton. Oh, so in this gamma ray, since a neutron turned into a proton, then there is an increase in atomic number by 1. So it makes sense that in the example given, cobalt 60 went to nickel 60, just because the only thing that we changed was the atomic number. In table 2.4, which is on page 59 of the textbook, we have the forms and properties of the nuclear radiations that I just explained. You can see the alpha with its symbol and its charge. Also, the same information for beta, gamma, and positron.